Thank you very much for the kind introduction. And also I thank the organizers for giving me the opportunity to have this talk here today. We are at a science festival about the apocalypse, so the end of civilization. So I think it might be fitting that we talk today about the end of science, which means that when we know all that can be known, what is left? There are a lot of obstacles to gain knowledge via the scientific method. And of course, there are a lot of such obstacles that are set by the laws of nature. And for example, you cannot know what was before the Big Bang, although Stephen Hawking famously said, or written in his famous book, that the question what was before the Big Bang makes as much sense as asking what's north of the North Pole. So it might be that such questions turn out to be having no sense, making no sense at all. We cannot look beyond the cosmological horizon, which is the border of our observable universe. We cannot look into the interior of black holes. Actually, we can, but if you jump into a black hole, you will never come back. You can't tell of your experience. There are, or there might be, parallel universes that we could explore, or maybe we cannot explore. We can only see the impact of parallel universes in quantum mechanics. So there are a lot of physical laws that prevent us to gain more and more and deeper knowledge. But what I want to talk about is which are the frontiers set by the laws of rational thought or the scientific method itself. And for this, I want to present you three, let's call it mysteries, which might still present as mysteries for many, many future generations to come. So the first mystery, Mary's room. This is a thought experiment. So it's not like that you actually implement the experiment, it just needs to be conceivable. Mary's room is the story about a brilliant neuroscientist. She's so brilliant, in fact, that she knows everything about vision and especially about color vision. And as I said, this is purely hypothetical, so she really knows everything. Everything there is to know about vision. Not just what we know now as the scientists, the neuroscientists, but everything we can ever know about the physics and the chemistry and the biology and so on of color vision. And she knows that because she is afflicted with color blindness, total color blindness. She cannot perceive the world in colors at all. Everything she sees looks like this. And I invite you to look a little bit more closely at this picture and imagine you are Mary and you know everything about color vision, but the world, this butterfly, looks to you like this. Now what happens if one day she is cured and wakes up and sees the butterfly like this? She learned something new. She learned something that in all of her studies she could never ever learn, namely how color looks like or how it feels to perceive color. And this experiment should show you that there seems to be an explanatory gap between physical knowledge and, well, what it is like to see color. So what is the subjective perception of color or subjective perception in general? And to close this explanatory gap, some argue, might be impossible. Although there are ways to attack this thought experiment. For example, one premise is that it is inconceivable that through her studies she might learn how color looks like. When in fact, again, this is hypothetical, maybe if you tell her in a very, very long description how blue, the color blue looks like, she will have learned how it looks like. Because this experiment is hypothetical, it might not be unconceivable at all. It just fights our intuitions. And also, maybe the question does not make sense at all, because subjective perception, also called qualia, is like to brain function what heat is to molecular motion. So, in fact, it is all physical or material, and it is explained in a way that is sufficient, but it's just two different concepts. Let's go to mystery number 2, the Sleeping Beauty paradox. This is again a thought experiment. And the subject now is not Mary, but the subject is Sleeping Beauty. And there's an experimenter, and the experimenter at the beginning of the experiment throws a coin. And when it lands heads, Sleeping Beauty will be woken up on Monday after she's gone to sleep on Sunday. And she will, upon awakening, be interviewed. If the coin lands tails, she will also be woken up on Monday and interviewed. However, she will be put to sleep again and be woken up again on Tuesday after, and that is important, being given a drug that prevents her from having any memory of the earlier awakening. So far, so clear? I hope. Now the interview, on each awakening, she's interviewed. And she's asked the question, what is the probability that the coin landed on heads? Now we should ask ourselves, what should she answer? So, let's put ourselves in the shoes of Sleeping Beauty. She's woken up, but she does not know whether it's Monday or Tuesday or the coin has landed heads or tails. But still she can reason while having this degree of uncertainty. And there are two possible ways to do that. One way is as follows. She knew that she would be waken up all along. So she gains no additional information at all. So the probability that the coin landed heads is 1/2. The second way to look at it, well, she can be in 3 situations. She does not know which. It could be either Monday and the coin came up heads. It could be Monday and the coin came up tails. It's Tuesday and the coin came up tails. All are equally likely, and what do we know when we want to compute probability? 3 events equally likely. The probability that the coin came up heads, which only happens in 1 instant, it's 1/3. So there are 2 different answers. And that is a problem because in science we're used to working with uncertainty. But if we know all of the parameters, we can determine this uncertainty with certainty, which in that case it seems we cannot. And also some people might argue that this is an open question forever. We might never know what probability actually means, or uncertainty. Mystery number 3. The continuum hypothesis. Now this is again mathematics, but don't be afraid. This is about the infinite, about infinity. Now let's talk about finite things. There are finite collections of things. Here I have 2 examples. There are 5 words from the English language, bird, cat, dog, fish, moose. And there are 5 letters, A, B, C, D, E. How do I know that those 2 sets, you call them in mathematics, have the same cardinality, you say in mathematics, so the same size? How do I know those 2 collections have the same size? Well, one easy way to do it, you put them next to each other and compare them. You find a 1-to-1 mapping between them. Now you could ask, man, why didn't you just count them? Well, it's the same thing. You map them to 1, 2, 3, 4, 5. You map the other set to 1, 2, 3, 4, 5. And you can acknowledge that you can do that. So those two sets have the same cardinality. How do I find out that one set has a smaller cardinality than the other? Well, that's also quite easy. I map them, and when I fail to map them, I got always members of the second set, the second collection left. Then I know that one collection has fewer items than the other. And this has to be the case for all attempts to do this. So then I know, and I see, I can prove that the set bird, fish, moose has less members than A, B, C, D, E. Now, those are finite sets or collections. What about infinite ones? So one set that I hope you all know is the set of integers, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. I can always find a number that's greater. And what you can do is you can set them side to side with all of the even integers, 2, 4, 6, 8, 10, and so on. But also with all the odd integers, 1, 3, 5, 7, 9, and so on. And all the positive and the negative integers together. Now this might seem very, very strange, because if you take the odd and the even integers together, you get all of them. How can that be, that I take two different sets and I get just as much as I had before? Well, that's only possible if you have infinite ones. Now it gets a little bit more complicated. Maybe I have to ask how many minutes I have left.
10.
Oh, 10.
No, 10 when you want to 10-minute Q&A.
Ah, I see. Okay. 10 including Q&A, so I will explain a little bit more quickly.
15 minutes left. You have 15 minutes left. I'm sorry.
All right, 5 minutes left. Okay. So, you can see that the positive integers are just as many as a subset of all of the numbers that exist between 0 and 1. What do I mean, all of the numbers that exist between 0 and 1? Well, you can imagine a continuum, like on a large line, and I have 0 and I have 1 and all the numbers in between. And all the numbers in between are, for example, numbers like 1/3 or 1/2 or 1/8, but it could also be like a weird number, like a square root or something. But all of the numbers. Now the thing is, you can prove that there are not as many positive integers as there are such numbers on the number line between 0 and 1. How do I do that? Now this is a bit of a mind twister here. It's called reductio ad absurdum. It's a logical device. You assume that what you want to prove is, you assume the thing you want to show is false. You assume that it is actually true. So what do we want to show? We want to show that we can count all of the numbers between 0 and 1. Let's assume that this is true. Then such a listing would look like this. Now there are a lot of numbers I did not specify. They are called A sub index 11, A12, A13, A14, and so on. Those are all the digits of all the numbers I assume I have listed. Let's assume that we can actually do that. Now let's have a special look at this diagonal here. And then we create a new number, X mystery, which is constructed in such a way that if I am at the position number 100, say, and if the diagonal happens to be 4 at that position, I will define the number to have the value 5 at this position. And if it's not 4, I say it's 4. Now the brain twister here is, ask yourself, this new number, can it be in the set that I have listed? No, it cannot be in that list, because I've constructed it exactly in such a way that it could not have been in that list, whatever that list looks like. This is a contradiction, and when I have such a contradiction, this means that the premise was wrong. I cannot list all of the numbers on the number line in such a way that I can map them one-to-one on all the integers 1, 2, 3, 4, 5. So if you want to have maybe something more tangible, if I have the continuum like a line, there are many, many more numbers on that line than I have counting numbers 1, 2, 3, 4, 5, and so on. Now this is not the problem, this is not the mystery. The mystery is as follows. Now I know there are different kinds of infinite. There are sets that are infinitely more than the already infinite integers. So the natural question, at least natural for mathematicians, is, well, what infinities are there? Maybe there is a set that has more members than there are integers, but less than the real number line. Does such a set exist? Maybe you can make up your mind thinking about, okay, does it exist, does it not exist? Mathematicians have struggled with this for a very, very long time. And the result was, there is no solution. In the sense that if I take the axioms of set theory, of, in a way, all of mathematics, I can neither prove nor disprove the continuum hypothesis. It's impossible. Mathematical logicians have proven that it's impossible to prove or disprove this fact. It's something that you can, actually something that you can believe in or not. So, we have 3 mysteries. One is, can we ever understand with the help of physical facts, with physical knowledge, what it is like to be Mary? Or how Thomas Nagel put it, how it is like to be a bat? Can we ever understand with certainty, model with certainty, what uncertain events are? What probability actually is? And the third mystery, what is the infinite? Does it exist in some way, or is it just something that we have made up with mathematics? Well, thank you for your attention.